Good evening, everyone, and welcome to our special edition Science Cafe this Wednesday evening. I'm your host, Chris Smith, and I work here at the North Carolina Museum of Natural Sciences. It's good to be with you all. Thank you for tuning in to this special program. We've got an exciting show for you tonight because we have some very exciting and very special guests with us here, actually inside the museum. How much fun is that? To give us a little bit of their knowledge, experience, insight, and expertise onto, well, the solar system, the universe, the birth of the planets, meteorites. You're going to want to stick around for this show. To get us kicked off, I want to introduce everyone to the first person you'll hear from, who then will be introducing tonight's special guest. But before I do that, Dr. Rachel Smith, I need to remind everyone that whether you're watching on YouTube or over on Facebook, you can participate in tonight's program. You do that by leaving your thoughts, questions, comments in the chat as we go throughout the program. I've actually got those pulled up. I'll be taking a look at what's happening in the chat. So at the end of the presentation, I can actually moderate your questions back to our guest speakers, and we can have a little bit of conversation and dialogue about tonight's topic. So jump on in the chat. We're going to have a great show tonight. Now, to introduce tonight's very special guest speaker, I want you all to meet the head of the Astronomy and Astrophysics Research Lab here at the Museum of Natural Sciences and a professor at Appalachian State University, Dr. Rachel Smith.
Thank you, Chris. Thanks, everyone, for being here. And I'm so excited. I'm Rachel Smith. I'm here at the Museum of Natural Sciences at an empty cafe. So hopefully sometime soon we'll welcome everyone back in person. But today I have a very special guest, a good friend who I've known for a long time. His name is Dr. Denton Ebel, and he is the curator of meteorites at the American Museum of Natural History in New York City. And he's also the division chair in the Department of Earth and Planetary Sciences and a professor in the Richard Gilder Graduate School at the American Museum of Natural Sciences. And I'll just say quickly that I've known Denton since I was a first-year graduate student at UCLA, and he came to our opening of the Nature Research Center, where we are right now, in 2012. So he's been a friend and a colleague now for a long time, and so it's really great that he could visit us and tell us all about meteorites and planets and his great expertise. And so without further ado, I would like to start with Dr. Denton Ebel, who will tell us about dust to planets, clues from meteorites. And thank you all for coming.
Thanks, Rachel. That's great. It's great to be here in North Carolina, down from New York City. At the American Museum of Natural History, we also are not doing live shows like this yet, but we certainly are doing great programs like this one online. I want to talk about meteorites. I study meteorites, but we're going to start in a program called OpenSpace. OpenSpace is a software tool that you could download your own self if you have a strong computer, such as the one Rachel's using now, to drive in OpenSpace. We can look through the entire known universe, galaxies, the cosmic microwave background, but we're going to focus today on the solar system. And we're starting at home with the Earth. The Earth is a great planet. It's a beautiful planet. It's a unique planet. As far as we know, there's no planet B that we can go to. And you'll see in OpenSpace, we're back in 2011 when we didn't have good coverage of the North Pole that we could show in this view. So what we're showing you is data from many, many space-based assets. In this case, from satellites. We also have data from rovers. We have a big pink cursor to help us get around. Right now, we're seeing the trail of Earth as a blue trail. We're seeing Jupiter and its moons in the background passing by. We're seeing the solar system in its architecture. And if Rachel can tilt us down so we can see it from a more planar view.
Other way?
Either way, we can go up, we can go down. The solar system doesn't care whether we go up or we go down. And we're zooming away from Earth, and we're seeing the trails of the planets. The Earth, of course, is surrounded by the trail of the moon, which you can see as an orange trace. In the distance, we see the galaxy itself, the plane of the galaxy, and the galaxy is also a disk, and the Earth and the solar system are rotating around the center of the galaxy at a very long period, 250 million years or so. Now we're starting to see the other planets come into view, and I'm going to ask Rachel if she can make the planets bigger. So now she's increased the sizes of the planets in open space by 3,000 times. And you see the planet Jupiter. Planet Jupiter is actually larger than all the rest of the planets put together. And we see Saturn. These are the two gas giants that are outside of the four innermost terrestrial planets, or rocky planets. And then we're starting to see Uranus and Neptune come into view. And as we pull out even further, Rachel's going to turn on the trans-Neptunian objects, the cometary bodies that rotate around the sun, that orbit the sun by the force of gravity beyond the orbit of Neptune. And there's a small number of them, because we haven't discovered nearly all but a small subset of these objects, and you can actually see that they're clustered along certain lines of sight where we've got better observations than others. And some of them have very strange orbits. And if we look at the disk edge on, we see that these objects are weakly bound to the sun, and they're also small, and so they have very eccentric orbits, many of them, including Pluto, which has a very strange orbit compared, for example, to the ice giants Uranus, Neptune, or the gas giants Saturn and Jupiter. So we're going to talk a little bit about comets. They're primarily made of ices. They are orbiting so far away from the sun that when they formed, the constituents that could make them were particles of ice. So let's turn off the comets. We've had enough of comets.
Oh, okay.
We're done with comets. Occasionally, comets get perturbed in their orbits and come near the Earth, and they make spectacular light shows, and I'm sure you've heard about them before in a Sci Cafe. If not, look them up. But now we're going to make the planets smaller again, and we're going to zoom in on Saturn, because one of the cool things about this disk of the solar system with all these planets orbiting the sun in an ecliptic plane is that it mimics the galaxy, but also Saturn itself and Jupiter mimic this. So as we come in close to Saturn, we're seeing all the minor moons that have very strange orbits that are very loosely bound to Saturn. And again, most of these are icy bodies. And as we go closer and closer, we see, if we tilt it so we see the plane, and we can actually turn on time. So in open space, we can take time and move it forward at a fixed rate. So we're going to go at about, 5 days per second here? Now we're seeing the moons racing around. The inner moons, of course, moving much faster because they have, because of their angular momentum, and the outer moons moving slower and slower. And the inner moons and the disk of the rings form a very tight, flat plane relative to the outer moons. So the outer moons are sort of like the comets were, as we just saw in the solar system. And the inner moons and the rings themselves form a very tight plane around Saturn. And the rings, which are always very, very, very cool to look at, I hope some of you have seen them through a telescope. Perhaps that's a question in chat. How many have seen Saturn's rings through a telescope? And this is how we depict them in open space. We're moving rapidly. Ooh, now we're seeing the shading of the rings by the sun. So the sun would be in your upper right corner of your screen, and you're seeing it shade the rings. But the rings actually transmit light around because they're made of water ice primarily. And this is a clue to their age because they haven't been polluted by rocky materials very much. And we discovered this with the Cassini orbiter that orbited Saturn for 13 years. So let's zoom out and maybe turn off time because we don't want the planets to go speeding around. and we can see Saturn's orbit there as the yellow trace coming down from the top of your screen, and you're seeing Saturn's moons. And we're going to move inward in the solar system, and we're going to see the solar system as the ecliptic plane that it is. So zoom way out and start to move towards the sun as center, I think. So there's Saturn and its nest of moons. The whole Saturn system is incredibly complicated. A lot of things going on there dynamically, and so is Jupiter. Now let's move towards the asteroid belt.
Focus.
The asteroid belt is mostly between Jupiter and Mars. So you can see Jupiter's and its moons, and now you're seeing the outer belt, the inner asteroid belt. We don't have enough bandwidth actually to show the entire asteroid belt. We have thousands of asteroids within open space, and it would ever slow everything to a crawl. But we would like to show also the asteroids that cross the orbit of Mars. That's the red.
I have to turn them.
Nope, it's not the red line.
That's red.
It is red, but the blue
No, I have to
line
turn
going
them on.
around the around the.
Hold on.
Okay, hold on. So the red ones are the Mars crossers,
Yes.
and the ones in turquoise are actually the asteroids that are in open space that cross the orbit of the Earth. And these are the asteroids which are potentially hazardous to the Earth itself. If you can cross the orbit of Earth, it's like a buck that can cross the highway. It's a hazard to your car. And so in this case, we're showing those, and you can see the red trace of Venus and then the blue trace of Earth, just barely. And can we turn on time?
I did.
Just a little bit. Are we going at, what, 100?
5 days a second.
5 days a second? Can we go faster?
Yep.
Oh, they'll start whizzing around the sun, these asteroids. But you know, the Earth is a small target, thank goodness. And space is really big. So we're not worried so much about them. But what the asteroids do is they drop little rocks here and there, and those rocks get thrown into the inner solar system by the action of Jupiter, and they fall to Earth as meteorites. And as you can see, there's no real reason why they'd fall anywhere in particular on the Earth, given that space is big and things are fairly random in the sense of where these rocks are in space. But these rocks, the meteorites, but also comet material and even interplanetary dust, form the clues that we have in our laboratories on the Earth, which you can come visit at the museum here in North Carolina or at the Arthur Ross Hall of Meteorites at the American Museum of Natural History in New York. And they tell us about the solar system and its beginnings and about the planets, because some meteorites come from planets. We also now are sampling asteroids that are actually near-Earth asteroids like these turquoise ones whose traces you see. Why? Because they're easy to get to from the Earth without spending a lot of energy on rocket fuel. So I would like to now segue to some slides. And I know OpenSpace is super cool. Look at all those colors of all those asteroids. But we want to segue now to a little bit about what the asteroids actually tell us, what meteorites actually tell us. I'm going to start with the elements themselves. So these are the elements in the periodic table that you're familiar with from high school chemistry. The galaxies began this galaxy about 13 billion years ago, mostly helium and hydrogen. As stars formed, red giant stars that exploded to make supernovae, other elements were made within the stars by the fusion of helium, or hydrogen to make helium, and helium to make things like oxygen, carbon, and nitrogen. And finally, all the way up to iron, and then the elements beyond iron forming in supernova and stellar explosions, which we're only starting to understand in the last few years, in fact. And all these elements form clouds, molecular clouds in space, and they gravitationally collapse by their own gravity to form nebulae, or solar nebula accretion disks. And we can actually observe these far away in our own galaxy in star-forming regions today. So on the next slide, this is showing the Orion Nebula. And we see on the upper left, we see a disk of dust and gas around a sun, which is white in the middle. And we can't see through the dust to what's behind it, so it's black. In the middle right, we see a disk that's embedded in a cloud core, a core that's still collapsing to form the disk, but is also being blown away by large stars with huge stellar winds that are nearby in this birth-forming environment in the Orion Nebula. So we see these things far away using telescopes like the Hubble Space Telescope, and we can also model the processes we think are happening with astrophysical models. So if we go to the next slide, we have a model on the upper part of this slide. We have a conceptual model which we can attach numbers to and think about in terms of hydrodynamics, which is the physics of how fluids, including gases and particles in gases, move. We also see jets going from the central stars of these disks. And this is a very broad view. And in falling dust and gas things are happening. We're only beginning to understand how those things happen by observation and by modeling. But what we have in our laboratories, what falls to the Earth as meteorites, what we can collect in the top of the atmosphere, and what we can actually sample from space missions are main belt asteroids, asteroidal material from inside the near solar system, but also cometary material from comets that come in and we sample as they go by. And that's on the outer solar system, the trans-Neptunian comets. And these constitute clues that we can actually hold in our hands, put in our instruments, and look at using electron microscopes and other tools at our disposal today. So I'm going to talk about some of those objects and what they tell us. So this is a slide encapsulating what we learned a little bit, well, not what we learned, but how we sampled comet material with the first mission to return samples from a comet or from any solid samples from space to the Earth after the Apollo program ended, the lunar sampling program. So these were the first solid samples, and they were collected in the upper left. You see an artist rendition of how it was collected on the aerogel tiles. Aerogel is a silica foam, sort of like the head on a beer, but made out of kind of a rock. And on the bottom right, these are particles shot into aerogel at 6 kilometers per second as we collected them in an analog experiment. And on the left, the bottom left, is a picture of a little tiny piece of aerogel with a 1 millimeter long track in it. You can see the track goes horizontally. And this is what we studied in the lab from a comet. We did some of that work actually at the American Museum of Natural History, but I'm not going to talk about that right now. The next slide is summarizes another kind of material that we study. There is actually at the Johnson Space Center a curator of cosmic dust. And what that person is responsible for are these small particles collected with repurposed aircraft that collect at the very highest parts of the stratosphere that we can reach. And we can collect both asteroidal, interplanetary dust particles or ones from comets, and we can tell the difference by how they release noble gases, but I'm not going to go into that either. So all of these materials have something in common. They all have compositions that are very much like what we see in the sun, minus the helium and the hydrogen. So if we go to the next slide, this is about meteorites that are a lot like those particles. This is a classification scheme for meteorites. Oh my goodness, look at all those boxes. What a mess. You don't have to memorize this. There's no test, no quiz after this. What's important here is we have two basic types of meteorites here. We have chondrites on the left, exemplified by the Allende chondrite, which fell in Mexico in 1969. It fell. People picked it up right away. So it's contaminated by terrestrial rain and snow and dust and water and so forth. And we have differentiated meteorites on the right. So these are from planetary bodies like Vesta or Mars, but these ones were completely destroyed in the early solar system by impacts. And so where it says Vesta, Vesta is a asteroid that was impacted fairly strongly, and we have rocks. I'm going to show you one from the asteroid Vesta. The largest asteroid in the asteroid belt is Ceres. The second largest is Vesta. We also have samples from Mars, but we only sampled the thinnest crust, the gray part there of the planet Mars. But those rocks tell us a lot about the planet Mars. And then as these bodies were broken up, we got to the core of the matter. And we have samples of iron meteorites that come from the cores of those planetary bodies. So if we go to the next slide, I'm going to talk about the elements again. This is chemistry. And all our chemistry, a lot of it we learn about from looking at the sun. So the solar photosphere has a spectrum. You see, we go from red on the right to orange to yellow to green to blue to violet. Roy G. Biv. The spectrum of the solar photosphere, we can see that if we take a solar spectrum with a piece of crystal glass. But there are lines that are missing, and these are lines that are absorbed, light that is absorbed at certain wavelengths, that means colors, by elements in the sun. And using spectra of the solar photosphere, we can see what the abundances of elements is in the sun itself. And this is what this chart at the bottom shows you. And see the difference between the hydrogen, the most abundant element, 10 to the 11th atoms per 10 to the 6th silicons. That's 6 zeros, big numbers here. And then far to the right, the least abundant elements, which are decaying actually all the time, thorium and uranium, they're very, very low abundance indeed. And so you can see why gold is so valuable. Not only is it abundant, very, very low abundance, but it also goes to the core of planets when they form. And you can see on the left that the sun, the big orange ball, is huge compared to all the little tiny little planets, Jupiter and Saturn and so forth. The sun, solar photosphere abundance is the abundance of the solar system, because that's the sun, and that's what most of the stuff is in. So if we go to the next slide, we see the importance of the chondritic meteorites as telling us the abundances, because we can measure them in the laboratory better than we, until recently, could measure them in the sun. And how did we know we were right measuring them in the sun? Because we see them in the meteorites. And for most of the elements, there's a perfect correspondence between the elements in the sun, the solar photosphere, and what we see in the meteorites. I've only labeled a few elements here, uranium at the bottom left, and you can see oxygen, carbon, nitrogen, hydrogen, much more abundant in the sun because they're gases, they don't make rocks. Well, oxygen makes rocks, carbon can make rocks, even hydrogen can make water in rocks bound in minerals. So we do have some in the rocks themselves. And the other thing to note here, magnesium, silicon, iron, and sulfur. Magnesium, silicon, and iron are each 10 times more abundant than calcium, aluminum, and nickel and sodium, which are also important. So in the next slide, this is some work that I do. I take a piece of the sun and I cool it in a computation, a chemical calculation, so I can hold it in my hand. I impose a pressure of the hydrogen that's in the atmosphere. And as I cool it, I get solids. Just like if I was to cool the vapor in this room, I'd get water, condensed water, like in your bathroom on your mirror. But here I'm cooling from very high temperature, 1800 Kelvin. That's, what is it? 1600
hot.
centigrade. Very hot. And I get corundum, aluminum oxide. I get calcium, titanium oxides. I get calcium, aluminum, titanium oxides, and start to get magnesium and silicon condensing as minerals. And then once magnesium starts to condense and silicon, I get magnesium silicates, which was what the mantle of the Earth itself is made of, and pyroxenes and olivines. These are minerals that are common in the cosmos. And I also get metal alloy. Can you show them the metal alloy up there? That's very important because the iron-nickel alloy is going to form the cores of planets. But here, these meteorites didn't come from bodies where there was a core. So the iron and nickel are still in the rocks themselves in the same abundances as we saw in the sun. Can you go back one? Mm-hmm. So you see iron and magnesium and silicon are all at the same abundance in these rocks as we see in the solar photosphere. But let's go to meteorites. There we go. This is the evidence. So what we see in these chondritic meteorites is the building blocks of the planets themselves, the building blocks of things in the solar system before we made cores in their interiors. And we see little tiny white things which are calcium and aluminum rich, and we see lots and lots of, this is a little bit rusted, this meteorite, because this was found on the surface in Texas where it had been rained on and so forth. We see little round things which are called chondrules, and they're magnesium and silicon rich. So now I'm going to go to another set of slides. These slides illustrate some of the work we do using the electron microprobe and electron microscope instruments. These are element maps. I'm sorry it's a little dark. Perhaps you want to brighten your screen. On the upper left, I'm showing magnesium, aluminum, and calcium. These are elements, fundamental elements that make up these rocks. Silicon is there, titanium is there, and there's iron as well. What you're seeing are different components, little fragments that consolidated together, free-floating in space, and then forming a sedimentary rock with a fine-grained matrix in between things, and little rounded melted droplets. A beautiful one with bars of olivine, red bars right there, and then another object below that, which is a fragment of a melted calcium aluminum rich object. And these objects, when we discovered them in this meteorite Allende that fell in 1969, there were large ones that we'd never seen before. And when I showed you that slide that said the solar system is 4.5 billion years old, those rocks actually tell us that the solar system is 4,567.8, roughly. 1,000 million years. So 4.5 billion, 4,500 million years old. And we learn it from these rocks. So I'm going to whiz through in the next couple of slides because they're pretty pictures. This is another kind of chondrite. We've outlined many of these objects. Look at how many of these things forming like a sedimentary rock that we can understand, and we study these rocks and how many of this and that thing there are in these rocks using these kinds of outlines. And if you go to the next slide, we can correlate these rocks back to the temperatures at which these different components form. So these are the earliest formed objects. We're trying to understand how old they are, how they came together into these rocks, and how these rocks then built hierarchically the planets themselves. And so on the right, this chart showing the condensation is showing the calcium aluminum rich stuff at high temperatures, and then the olivine, the red stuff, and the darker red stuff, the magnesium silicates with different ratios of magnesium to silicon that form these objects, most of the objects that we think were the original objects in the planets. And what happens when we put them together to make a planet? Well, what happens is we differentiate the body. So let's go to the next slide. So these are the differentiated meteorites that come from, we know some of them come from the asteroid Vesta. We know some of them come from Mars, the planet Mars, the surface of Mars. We know many of them are different kinds of iron meteorites, and some are stony iron meteorites like Hecata in the middle, which has crystals embedded in a metal matrix. So let's go to the next slide and see some of these up close. So on the top, we see Bella Rocca. This is on display at the museum. And we see the iron metal. But when the iron liquid went to the core and cooled, it had sulfur dissolved in it. Remember, sulfur was a very abundant element as well. Sulfur doesn't want to be in the iron. The iron doesn't want sulfur in its crystals. So little blobs of sulfur segregated out. And those are very important in dating these rocks and in dating, in fact, using uranium-lead dating of all solar system objects, but I don't have time to talk about that now. Below it, you see Huckata, again, a meteorite that's on display within the museum. And this is these are cut slabs, and here you see crystals of magnesium silicate embedded in iron metal. So this comes from somewhere in the interior of a planetary body that was disrupted. On the right, you see Johnstown. This is part of the Vesta mantle. And on the outer part, where it's not cut smooth, you can see a dark fusion crust. This is the material that froze as the rock was coming through the atmosphere. And that last bit of glass that was the liquid froze. And that's what the fusion crust is on a meteorite. And here you see that there's a lot of green minerals. These are magnesium silicates. So these are differentiated bodies. Can we go to the next slide? And what they tell us about is the cores and mantles and crusts of bodies in the solar system. So we know about these bodies, these planets, from the rocks that come from disrupted planets and also come from Mars and Vesta and bodies like planets and even the moon that were formed early in the solar system. But here's a mystery. The next slide. We knew from its mass and it's how it orbits the sun what the density of Mercury is. And we were very interested in understanding it because if we take the chondritic abundances of Earth, of the sun, and these meteorites, and we take, okay, we're going to make this much magnesium silicate and this much iron because that's how much we've got. We can make the Earth and the core is about the right size. Don't forget, iron is much more massive, dense than silicon and magnesium. And so we understand that. But we look at Mercury. Look at Mercury. The core is almost 70% of the mass of Mercury. Where did that mantle of Mercury go? How did it disappear? Was it broken off by some giant impact? But how did that happen? Or is the inner solar system where Mercury sits so different that there was a process that was gradual, that happens in every solar system, that things that form near the sun are in fact different, fundamentally more iron-rich. So we went to Mercury with a spacecraft because you learn by going. We've found that out the hard way. We went to the moon, we found stuff we didn't know. We went to Saturn, we learned all kinds of things we didn't know. The first time we flew by Jupiter, we were surprised to find all these different moons with different characteristics. We didn't know that. One was the most volcanically active object in the solar system. We didn't know that before Voyager. So everywhere we go, we find new things. So we go and we learn. So now we're going to go back to OpenSpace and talk about the MESSENGER mission. So MESSENGER, it's a long acronym, which I won't repeat here. You can look it up on Wikipedia. MESSENGER has a huge sunshade. See it on the left? And solar panels. We learned how to actually solar sail the spacecraft to save fuel. We got an extra month of mission from that. Engineers that designed the spacecraft, that flew this spacecraft, unbelievable. Great, great team. The engineers that do all this NASA work are amazing. The sunshade had to face the sun all the time, but it had a little pinhole in it that we could see what the X-rays from the sun were doing. We flew to Mercury, we entered Mercury's orbit, and we were in orbit around Mercury for 4 years. A lot of orbits. And what you're seeing in these tracks are the orbital tracks, but we don't have time to show all of the orbital tracks. You're seeing Mercury's orbital track around the sun in the yellow line that goes down, straight down, and you're seeing the orbit of the spacecraft. It had a very complex orbit because it had to keep cool, and Mercury's surface reflects a lot of sunlight in the infrared as heat. And so the spacecraft went far away from Mercury to cool itself off before swinging around Mercury on first at 12 and then 8-hour orbital stretches. So we had to tell it what to do for each orbit, like a day or two ahead, or an orbit or two ahead at least. And so, what do we want to show them now?
Magnesium.
Want to go to magnesium, or do you want to go to the, let's go to the
crater.
crater.
Yeah. Right, hold on a second.
My script. So what we were able to do with this mission was to measure a huge amount of things. We had 14 different instruments. We were interested in how Mercury, which has a magnetic field like the Earth, unlike Mars and Venus, how that magnetic field interacted with the solar wind and with the sun's magnetic field as well. And we wanted to know what the surface looked like. How did Mercury get shaped? The cratering at Mercury must have been quite intense over the last 4.5 billion years. What we're seeing now, we saw the true color a minute ago. Now we're seeing a Mercury map, a magnesium map of Mercury. What the spacecraft was able to do was to use the X-rays from the solar source, so X-rays from the sun, to actually understand by X-ray fluorescence what the composition of the surface of Mercury is. And you can see the red colors, the hot colors, are where Mercury has a high magnesium concentration on the surface.
I forgot the crater. Do you want to go?
And the blue colors are where it has a low magnesium composition. And you can see there's lots of differences. What we discovered is that the reddish areas, the magnesium-rich areas, are lava flows, gigantic flows in many cases. And can we go to the crater? Can you remind me of the name?
It is Kainsaz crater.
Kainsaz crater, and I think that's your marker
That's it.
right there. And we could leave the colors on, but it doesn't have much contrast. We can take the magnesium map off. So we were able to map magnesium, silicon, and aluminum fairly well, calcium pretty well, and some iron. We got a sense of how the iron works. Oops.
Hold on a sec. I think I just stand by.
So I wanted to show you this one crater, which showed us a little bit about how we were able to learn a little bit more about Mercury's history by understanding the surface features of Mercury. Because after all, what we can see from the spacecraft is the surface. You know where you're going?
Yeah.
Great. Great navigation.
Sorry.
There you go.
I got to get around. Hold on. Sorry about that.
So what we had on the spacecraft was narrow angle, very focusy cameras, and wide angle cameras that could see lots of area. And as the mission wore on.
Oh, there it is.
Oh,
there it is.
yeah.
I got it. Sorry.
As the mission came to near an end, we were able to go closer and closer to the surface through, again, amazing engineering, where we were actually using the laser altimeter for navigation because radio ranging no longer could tell us accurately what the altitude actually was. You're coming in okay.
I know. I think I turned off a data set. So if you just hold on 1 second, I have to turn it back on.
And this is a crater that shows us several things. One, it shows us lava flows. It shows us how craters, one on top of the other, tell us the age relationships between cratering events in the history of the planet. And the cratering history of the solar system is fairly constant in the sense that there were a lot of big cratering events early and smaller as time went on. We also can see.
I'm
maybe
sorry.
We switch to the.
I have to.
Let's switch to.
I made a mistake.
Let's switch to the slide.
Okay. I can actually. You want me to go back to the slide?
Yeah, go to the slide. Next slide. There we go. So this is what the crater looks like. So this is imagery, and we can see in the green. Can you point with the pointer? In the green circles, we see superposed craters
there it is.
on the big crater that's in the yellow lines. And the big crater is most of the field of view. And we can see craters on top of craters. And what we see in the white area, right there, are ghost craters. ghost craters are craters that have been filled in with lava flows. And the orange arrows that point outward from the center there are showing the edges of lava flows that we were able to figure out are there. And we have 3 areas that are outlined in blue. And this was a discovery of the Messenger spacecraft mission, which was we were able to focus in on these called hollows. These are areas which we think are vents from which the volcanic material came that filled these craters, and the big crater is almost all filled with lava flows. And we can compare these filled-in craters with other craters that are not so much lava filled. Can we go back to the message?
Yeah, I'm trying to.
So what we were able to do with the magnesium, silicon, aluminum maps, and our overall picture of the volcanism at Mercury was to be able to use what we see at the surface to try to understand what is at depth. And to make a long story short, what we saw on the surface, the abundances of not only magnesium, aluminum, silicon, calcium, iron, but also sulfur, the radioactive elements, potassium and uranium and thorium, and things we could also measure somewhat like chlorine and sodium, we were able to actually understand a lot about the chemistry of Mercury, and that's the point here.
What do you want?
We have several hypotheses for how Mercury got the way it is. And those hypotheses, addressing those hypotheses by going and learning and measuring and observing and thinking, were why we did the mission in the first place, is to answer that question: why is Mercury so dense compared to the Earth and Venus and Mars in the terrestrial planet zone? And can we go to the last slide?
Oh, yeah.
And this is what we concluded. We've gone from meteorites, cometary dust, interplanetary dust, understanding the composition of the solar system, to understanding how planets differentiate, to understanding that the Earth has the right size core, pretty much. Venus has pretty much the right size core, given the solar abundances, and that Mercury doesn't. And we went there, and we tried to figure it out. Do we have metals separating from silicates, rocky parts, in the disk by some process that's common? Did we evaporate the mantle by a early and very hot sun and solar wind that was very strong, and then it blew away the mantle by evaporation? Then we'd lose all the sulfur, we'd lose all the potassium, we'd lose the sodium, because they're not refractory. They don't condense at high temperatures, they evaporate easily. Or did we not condense the silicates at all? They were simply still in the gas phase. Again, where is the sulfur? There's sulfur there, there's potassium there, there's sodium there. So we don't think, based on our measurements at Mercury, that these hypotheses work. Was the inner solar system enriched in carbon and hydrogen such that it was very reduced and it was a different chemistry than the condensation that we expect in the outer solar system? This is an idea that holds water. It fits with what we calculate and what we saw. Was the mantle stripped by a giant impact? We used to think that this would also strip sulfur and potassium and the volatiles, but that's not a strong conclusion anymore. But we would have to, models say, destroy the planet almost entirely, and then the gravitational pull of the remnants of Mercury would have to not be strong enough to pull back the rest of the rock. Mercury's orbit is 88 days, Earth days. So the remnants of Mercury would go around the sun in a cloud. Why wouldn't they just reform and stay pretty much the same composition as they originally were? So mantle stripping by a giant impact remains possible, but based on our measurements is less likely. So hypothesis 1 and hypothesis 4 seem to still be potentially strong hypotheses that are consistent with what we saw, and require us to understand more about processes in the inner parts of solar systems, not just here, but far away as well. So now I'd like to, Chris is going to moderate, and we're going to take questions.
Sorry, I messed up Mercury for you.
You didn't mess up Mercury at all.
The data sets get a little. I've been driving OpenSpace. What the audience doesn't see are the menus. And just so you know, we should tell people maybe you can go to OpenSpace, OpenSpaceProject.com, which we're both
not wearing my T-shirt.
Ko-Ai's not wearing his T-shirt. Bad, but I am not either. But you can go to this software. It's NASA funded and led by the American Museum of Natural History, and we're partners. And you can navigate the software. It's free. You generally need a pretty good machine like these Alienwares, but the data sets do get a little bit confusing. So what you didn't see was me trying to find the data set I turned off by accident.
Any gamers watching with a good video card can make this go easily. And
so
there's
apologies for that.
a whole Slack channel and support online for you to do. And by the way, if you come to the museum here in North Carolina, you can see some beautiful segments showing the Kuiper Belt, Charon and Pluto, and the cosmic microwave background, the Rosetta Comet, all kinds of things done in OpenSpace by Rachel and some
interns,
of the people
students.
who work
So it's really
here.
for everyone.
It's really cool.
You can drive around the universe.
Really cool. Okay.
Yeah.
Well, first I'll say thank you, Dr. Ebel, for your presentation. Thanks, Rachel, for driving. Actually, people were commenting. OpenSpace commented in the chat, and they said you were doing a great job
Thank
driving.
you. Probably that
Might be people from the Museum of
Thank
Natural
you,
History.
OpenSpace.
So great job from both of you. I'm sure everybody watching at home gave you a great big round of applause.
Thank you.
And they're dropping their appreciations in the chat right now. But folks, I'm turning to the chat now. I'm looking for your questions, and we do have a few that have come in. The first one, though, that came up early in the presentation was one of our viewers wanted to know what each of yours favorite meteorite was.
Oh.
Which you're both. Actually, I didn't introduce you, Rachel, with the title, but you're also the curator for meteorites here at NCMNS.
That's right.
So you're both around quite a few meteorites.
I've seen a lot of meteorites.
Yeah, that's like asking who your favorite pet is. And there are no favorites. But, I mean, it's interesting. I get asked these, there's some the more ordinary looking meteorites are actually the most interesting scientifically. And so I think my favorite one is Murchison because it has amino acids in it. It's one of the few meteorites with amino acids, and there's some extraterrestrial amino acids in it. And it's been studied a lot, but it's fascinating to know that meteorites have stored these molecules, and these molecules that are the building blocks of life, and what Denton alluded to, they can survive in space, and that really inspires the search for life in space. And we have these kind of capsules filled with these really interesting organic molecules that all life on Earth has too, and some really exotic ones that we don't even have on Earth. So I'd say Murchison's my favorite for that reason.
So this conditions my choice because you see, in 1969, the astronauts had returned these rocks from the moon, and everyone who had instruments paid for by the taxpayer at NASA was waiting to study them, but they had to be quarantined because they might have space bugs in them that would kill us all. So while the moon rocks were in quarantine, but just before that happened, the Allende meteorite fell in Mexico, a chondrite, which had these big calcium aluminum rich inclusions that were big enough that we could, using the instruments of the time, get their uranium lead ages, which I won't go into, but it's a very important data point. And then in the fall, while we were waiting for the moon rocks, Murchison fell in Australia. So these were both falls, so they're very pristine rocks from space. So I would have to say Allende would be my favorite.
So we have the pair.
Just because, and then, of course, the moon rocks gave up their secrets, and we learned about magma oceans on the moon. We learned about, finally, we've now learned about magma oceans on planets like Vesta, planetesimals like Vesta. The Earth and Mars had oceans of magma where things happened in the very early solar system. So a lot of that information came from that year, that all those samples, the lunar samples, Allende, and Murchison. And they actually is a carbonaceous chondrite, but it has very little carbon in it at all.
Okay, excellent. My favorite is the piece of Gibeon that's upstairs on the third floor here, just because it's here in North Carolina and I can visit it every day. My second favorite is the giant one in New York City.
Yeah.
I can't remember the
Anagito.
name,
So he likes irons. Yeah.
but it's just enormous. How could you not? Like
He's
that
got a
right?
magnetic personality, so he sticks with the irons.
Meteorite humor.
Meteorite jokes. I love these people. Okay, now we also got into a small but interesting chat about OSIRIS-REx and the asteroid Bennu, and you were talking about how these meteorites, they get to Earth and we use them to get clues about the early solar system. But what about these new missions that are going to space rocks out in space to get?
Well, this is an era of sample return missions, and we entered this really with the Stardust mission in 2000, which returned samples in 2006 from a comet. The Meteorite Hall in the Museum of Natural History in New York was reopened in 2003, and so when we had the opportunity with our new Gems and Minerals Hall and so forth, in 2019 to do some improvements, we introduced sample return as a part of the study of meteoritics. So we have spacecraft models of Hayabusa, which we already have. The Japanese have already returned from 2 asteroids sampling missions, and OSIRIS-REx is there, and of course Stardust. And the OSIRIS-REx mission went to an asteroid Bennu. It's a very small body, 500 meters in diameter, and we discovered all kinds of things. We discovered also how difficult it is to collect from asteroids, and that spacecraft is on its way back with samples. And this is a very dark asteroid, dark because it has very rich in organic material, and that material doesn't survive passage through the atmosphere very easily. It's very like charcoal almost. It's not like a rock, and so that material is best sampled in situ in space. And it's interesting because the mission sample scientist, there's only been one so far in NASA history where a mission had a sample scientist. Harold Connolly we were on the phone with him just earlier today for other reasons. So everyone's very excited for these samples to come back, and of course for the study of the Hayabusa samples. Hayabusa 2 now is under study in Japan and soon will be shared with laboratories around the world, because these sample return missions are global missions by humanity. They are not, of course, we take national pride in the OSIRIS-REx mission. OSIRIS-REx is another acronym. And Japan, of course, is very proud of their engineers and scientists who have made these missions possible. But the entire analytical capacity of the world is used to study these rocks when they come back, because there's tools in India and tools in Germany and tools all over the place that are unique and are the best tools to study some particular thing, like amino acids, for instance. And so those tools are the ones we should use for those precious samples.
Excellent stuff. Next one that I have here for you, Stephen writes, the electron scan images of the meteorites that Dr. Ebel showed are beautiful. They could be enlarged and shown in an art museum. Are the colors in the slides a natural color or added by computer?
So what we've done is we can, using a rastering program, we can get the intensity of X-ray emission by magnesium, calcium, aluminum, titanium, silicon, iron, sodium, at each point, and you can see the scale bar there. That map is probably at 5 to 10 microns per pixel, so it's a very high resolution. So you could print a T-shirt with this pattern. And we've actually shown images like this in a museum exhibit at my museum in New York. And go back one more. Yeah, so you see, they're beautiful. So that's basically, it's like a color palette for, you could show the magnesium map in black and white, or the calcium map in black and white, but if you show it in a color, magnesium would be brighter or dimmer depending on the amount of magnesium in this pixel. And so then I'm just making an RGB image, a composite image. And on my website at the museum, my research site, not my staff page, you can actually burrow deeply down into this technology if you like. We have information there about how to do this. I have papers that are accessible online that can.
And this wasn't part of a little art display, if I remember, in New York. You had it as part of like science as art.
We actually had, yes,
right?
it was Picturing Science was the name of the exhibition, and you may be able to find traces of it on the AMNH web space.
Excellent, thank you.
So this kind of work comes under the category of image analysis, and what we're trying to do is go from pretty pictures to quantitative data, and we have pipelines to do that. They're complicated, but they work.
So these images, while being pretty, it's kind of like reading a map of where each of these.
We're reading a map of the mineralogy and of the objects themselves, their sizes relative to each other, their shapes.
It's a little like the false color map of a planet, right? That you apply the color to.
Yeah. So if you had an elevation map where you had elevation by color, you would be able to see where the high and low places are, where the craters are. Yeah.
Okay.
This is chemistry.
Excellent. So, somewhat off topic, but really not. We were talking about Mercury and what Mercury is made of. What are your impressions of the geology of Mars and the Perseverance rover?
Well, Mars is a much more complicated planet in some ways than Mercury because it's still got a lot of active processes that are going on. We know there is an atmosphere, and the atmosphere has winds. We've seen and studied dust devils forming. In fact, our rovers have had their solar panels coated by dust and then uncoated by dust devils. So that whole story is very interesting. And we know that there's been huge sedimentation by wind and then removal of the sediments by wind in craters. So even the crater counting that we use on a place like the Moon or Mercury to actually get relative ages of surfaces may not be as valid on Mars because of the sedimentary fill of kilometers thick that can happen. We have sand dunes on Mars, and Mars had an active hydrologic cycle. We don't think that Mercury ever had really anything to, because it's airless body, so any water that came to the surface, gone. Same with the Moon. But not on Mars. And Mars had active water on the surface early in its history. But we think that Mars was sort of dying as a planet. It's too small. It has no magnetic field. It was sort of dying maybe 3.5, 3.8 million years ago at the same time that life was emerging on the Earth. The oldest life forms on Earth, the oldest single-cell life is found at that time. So it's a tale of two planets, really. And Mercury is yet another tale. And they're all complicated. They're all worlds in themselves, as are the giant moons of Jupiter and Saturn. Io is a world that's the most active volcanically in the solar system, but it's far out there, yet it's so active. We didn't know that until the late 70s when we flew by with a spacecraft and we saw volcanic plumes. I say we. It was a woman sitting at a computer, a primitive computer, back in those days, late at night, who said, I think I see a volcanic plume. And she went, sure enough, people said, yeah, that's right. I can't remember her name.
I can't either.
One of our viewers wanted to know what sparked your interest in meteorites.
I didn't even know anything about meteorites until I was in my second postdoctoral fellowship. I was studying ore deposits in my first postdoc in Toronto, Canada, nickel deposits, and in the laboratory and theoretically. And I got a call from a guy in Chicago, Larry Grossman. He said, I need somebody to calculate condensation in the solar system. Remember I showed you a slide? You want to go back to this? And that one, previous. And we wanted to calculate when liquids, remember those liquid droplets? Astronauts' tears form spheres. And so spheres are formed by droplets in space, and molten droplets are not on this diagram. You need to have other conditions. And what are those conditions that form the molten droplets we see in the chondrites? And so I went to Chicago to study condensation of the things we see in meteorites. So that's how I got involved in meteoritics. I was already a geologist, and that's another story.
Another story for another time. The last one that I see here, and we're just about out of time, where in the solar system would you most like to send a mission?
You know, I was
Mercury?
involved with the Messenger mission. I was privileged to be asked to write a chapter about its origin, its enigmatic origin, for the book Mercury After Messenger, which is a summary of what we've learned there, Cambridge University Press. And I would love to know the oxygen isotopic composition of the planet Mercury, which would require at least a lander, if not a sample return mission. It'd be a very complicated measurement for a lander to make. There are a lot of great things we could do with more missions. It'd be great to sample Ceres. It'd be great to get another comet sample. It would be great to go to Enceladus, where these plumes of water coming out that are immediately freezing and forming the outermost ring, well, the E ring of Saturn, or helping to form it.
The oceans
Those
of Europa.
plumes are sampling the ocean deep in Enceladus, the moon of Saturn. And if we could fly low enough where the water is dense and slow enough so we don't destroy everything we hit, we could sample that plume. It's right there for the taking. But that is an engineering feat that we haven't been able to accomplish. But the Europeans, the European Space Agency, was able to match orbits with Comet, the Rosetta mission, and not sample, but study that comet intensely as it approached and went around the sun. So I think we'll be able to do that mission. It's probably easier than sampling Mercury.
All right. Well, if this was a science cafe and everybody was here, I would say let's give our guests one more round of applause.
And
I'm
we
sure
would be
everybody
waving at our
home
friends.
Yeah.
is clapping along. And definitely, folks, you can drop little clapping hands emojis in the chat box to express your appreciation for our guests. Rachel, Denton, thanks for coming out to the museum late. Thanks for visiting Raleigh and sharing your knowledge.
Great place to visit.
Thank you all for coming. This was a lot of fun, as always, Chris, and thank you for moderating. And Matt, who's backstage doing all of this, our media, so thank you as well. And all of you for tuning in. And have a
Support staff everywhere. We salute you.
Absolutely.
So, folks, I'll remind you, we've got more great programs and events and live streams coming up in the future out of the Museum of Natural Sciences. As early as next Tuesday night, we'll be playing trivia. Next Friday, we'll be talking about hurricanes and flood safety. Listen, science, nature, we got you covered. Make sure that you visit naturalsciences.org, the museum's website. Check out the calendar of events. Find stuff that looks interesting. Sign up. Most everything is free, so you might as well sign up and tune in and join us. And make sure that you're following the Museum of Natural Sciences on social media. We're on Facebook, Twitter, and Instagram, all three as @Natural Sciences. Anything else? If folks wanted to follow your work, how could they do that?
Well, we have websites. We each have Denton, you have 2 websites. I only have the one because I'm not as important. But you can see kind of what we're doing. We don't always update those readily, but go to OpenSpaceProject.com to explore the software and just keep being excited about science and exploring your universe. And we're always here to engage people in some way, whether in person or virtually. So I'd say that.
Yeah, I would say thank you all for watching us, and thank you, Rachel, for inviting me.
Of course.
And thanks, Chris, for moderating, and thanks for the museum. I'm impressed. The building has evolved and lots of new things all the time, and just an excitement here that's really, really palpable.
Oh, great.
But I also will say that there's a lot of content at the American Museum of Natural History.
So go there first, I guess.
Our ology websites are
just kidding.
Lots of offerings, because we've all been busy creating virtual content during this pandemic. And I hope everyone stays well, gets vaccinated, and pay attention to not just my science and Rachel's science, but all of science.
That's right. And support your local museums. Thank you.
There it is. Take care, everybody. Stay safe. Keep your community safe. We'll see you again soon. Good night, everybody.
Bye.